So this is gonna be a little bit of a review for the problems you had in quiz 1, and I'm gonna add at the end some information I think might be important for you, especially related for interrupt, SysTick, and GPO configuration, but with alternative functions. If you want more information about the GPO, there is a GPO Word document that I sent you guys through Blackboard and Discord, so you can review that. Okay, so question 1. I don't have the exact question that you have for your quiz, but there's an example that we can use to know what mistakes to evade or what steps to follow so you can get the right answer. So first of all, we notice that, okay, registers, you're doing subtraction. Okay, that's important, especially if it has an S, because this S tells you that, alright, this arithmetic equation is going to have an influence in these bits. So yeah, be careful with that. The second part that I want you to notice is that the registers that we're using, since we're using the Cortex-M core, it means that they have 32 bits. So when you look at this hexadecimal numbers, I want you to remember that it represents a 32-bit number. So that means that even though we're just writing a 96 here or a C8 here, it means that on the left side, we assume that there are other bits, but they're zeros, so that's why we don't write it. But we know that on the left side here, there are 0, 0, 0, 0, 0 going. And again, it's gonna affect the final answer, because if you try to do this number in a normal simple calculator, it's gonna show you only this part, but it'll miss out all the values that we had on the left side. And that's gonna happen because at the end you're gonna have this zero is gonna borrow from this one. It'll become an assumed 2, and then you will have 2 minus 1, you have a 1, and then you have a 0 here, minus a 1, and then you have to borrow from the left side. And okay, this the circuit that you use for this type of problems, it appears on your lecture tree. If you don't remember, please review the slides for the lecture tree. So since we are limited in the amount of numbers we can represent, if we don't have the bits and we are around this area, we can cross to the left side. It will make our number negative, but we will have a value that we can borrow from. And so what will happen is that this zero that we have here will borrow value and it become an assumed 2, and it will have 2 minus 1. And you have to be careful because the correct answer here should be all the bits on the left side should have a 1, 1, 1, 1, 1, 1, 1. And even though the 0 here borrow from this one, it won't become a 0 because this actually represents a 2 here. It become a 1, simply a 1. So instead of E, C, E, you will have F, C, E. However, how can you prevent yourself from, doing this confusing part? Because you might get it wrong, you might put a 0, because it's possible that you get confused. So my recommendation will be, when it's subtractions, do the second complement. If you have subtractions, do the second complement, because that's the way a computer does the subtraction, and that's the best way for you to go about it. Let's see, so let's go. I have an example, part of the example here where you do the second complement, and you can see, okay, so the original value is, okay, R0 minus R1. So we're gonna take the value of R1 and we're gonna get the second complement of it. So this is the number. Remember that on the left side we have zeros and zeros and zeros, a total of 32 bits. And then what you're gonna do is gonna flip all those bits. So the 0 becomes a 1, the 1 becomes a 0. So all the zeros that we have on the left side, they're gonna become a 1. Okay, so then after that you're gonna add a 1. So you have 1, you do the addition, 1 plus 1, that becomes a 10, and so on. And okay, that's the second complement for that number. And yeah, this is the hexadecimal number. I wonder why I put that. I guess I wanted to know, for you to think, how will this hexadecimal number be represented? Oh, no. Sorry. This is the binary number. I would like for you to think, how is the hexadecimal number gonna look like? So on the left side, you have a lot of ones and ones and ones and ones, and then at the end, you have these numbers. So you're gonna have a hexadecimal number that's gonna be like X, F, 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 F. So it's gonna be F, 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 and then the last two ones are gonna be, let's see, this is gonna be an 8, and there's gonna be 3, and then everything else is F, F, and then 4 more F on the side. There you go. Okay, so that was this part. But you actually don't need to show this in the exam. I just want you to know, so you get used to converting that. You're gonna use that a lot in the lectures and, of course, in the quiz. Now we see this part, and we have the number. Okay, 96 is R0. So we have R0 plus R1, because we already got the second complement. That second complement makes this subtraction into an addition. So because basically what we're doing is we're making, okay, so R0 minus R1, and what we're gonna have is R0 plus the complement of the second complement of R1, which is gonna be R1 negative. This is what is going on. But I want you to understand that we are still being fundamentally the original operation, which is a subtraction. So when you try to do the logic for the C carry, you're gonna still be using the part of the chart that talks about subtraction, even though at the end we're just adding. Okay, so at this part it's gonna be a little bit easier, and you don't need to get confused. You won't get confused. And okay, so notice that this is the final number, and yeah, we get the F correctly. We don't get an E as we got with the other one, where you can get confused in there. Okay, so now we're finally gonna use the circle. So this is where R0 was original, this is R1. The result that we got is on the left side. Okay, so we know it's a negative number because it's on the left side of the border, of the 0 border. So, okay, it's not a 0, so it's gonna be, the bit is gonna be a 0. Now for the B, did it cross the bottom border? No, it did not cross the bottom border. I've noticed some you did not put this, but in case that you forgot, this is the most positive number and this is the most negative number that we can represent with these registers. Okay, so yeah, that's what we use to identify the bottom border. The bottom border is between the most positive number and the most negative number. Now the carry will depend, especially if we were doing subtraction or addition. So in this example we were doing subtraction and we did cross the 0 border, so our carry is gonna be a 0. Okay, so that was most for the first question. Well, question 2 was more about if you knew the concepts or if you actually wrote them in your crib sheet. These are the ones I recommend having or mostly view, because you're not only using it in the lectures but also in the lab, especially in the lab. And this one is important, especially for the next lab. It hasn't been posted yet, but I think it's important for me to talk about it. So imagine that this is the main file where you're writing your main code, and so you guys have had the lecture about cystic. So most of the time people prefer doing one file for the main code and another file for the cystic one. So when you try to do that, it's important to remember that you have to export the functions that you're using in the main, and to actually make sure that you write the import in the file that you are moving that to. If you don't, then the code is not gonna run. So another part is important for you to, be sure when you're writing about creating variables and stuff like that, to know how many bytes you're using depending on the operation. Because many of you, for example, for this case, wrote, oh yeah, it's saving this much space in this variable. But you cannot just say space, you have to say, is it a bit, is it bytes? That's important. And the other part was this one, where, wait, no, it wasn't this one, I'm sorry. And this one too, most of you had it right, I think, but I'm going to talk about it. So basically, Rn is renaming the number of the register, for example, in this case, register 11, to this variable name. So anytime we are doing like any other thing, for example, this LDR stuff, like instead of writing R11, we could say, okay, R0 is going to be equal to REG11, and that should work. Let's see what else. Oh, the last question was related to this. You guys, majority of you did have this part right, but I hope you guys noticed that you had more text besides the area part. You had a section that talked about if it was read only or if it was write only. That is important because it really changes. And this part, few of you actually explain it, but yeah, you have to say, okay, align 2 just basically aligns the location to this many bits. This can change, so you will have to say, oh, if it's align 4, that's 32 bits boundary. Okay, and you always need to have at least one area, one line, minimum, that's a minimum. And what else? We usually use this when we try to write for the RAM or the ROM. You have seen that in your codes, and you will be using it in your future labs, especially to write variables or make arrays. But for this question, I'm not sure if this is the exact problem. As I said before, I don't have the solutions right now, or the quiz examples. I took this one from an old quiz, so this might have different steps. If you're using this to compare your answers, then I would recommend you to do this step by step, and I will be explaining that in this. Okay, so first of all, you have the contents, then you have the initial location of the SP. So this is the stack pointer. It's very important to know the location so you can find that when you're doing any programming Kale, and I'm sure you might have questions about this in the exam or in the quiz related to SP pointers, so be sure to don't mess this one up. Okay, so I'm gonna go step by step from the beginning until this point, because I remember the question was to give the solution of the stack, how the stack was looking after the point A. So you were to show what was happening after this was executed. Okay. So related to the last questions, the question 1, where you actually have to take into account the size of the registers, you have to remember this represents 32 bits. So at this point, most of you had it right. The only thing that you were messing up was that the base is supposed to always be empty. So the initial point is this one. This is where the SP stays at the beginning, but that should be empty. If you're gonna add another content, then you need to make sure to go to the next lowest address. Few of you actually put the address. I'll recommend putting that. Usually when we're grading about the stack, recommend that. You don't need to memorize this location. It's usually given, as it was in the quiz. Now it's important to know the order, because many of you put R6 at the top and R0 at the bottom, and then the other ones around it. You need to take into account that the lowest register, actually let me put it here, highest register goes first in the highest address. we always go from highest, which is the base of the stack, to the lowest, which is at the top of the stack. So when we try to go up, we try to subtract number 4 from your address, hexadecimal address. This is very important. Why 4 exactly? Well, because we have 32 bits, which translates to 4 bytes. And what is 32 bits? That's the content inside of the register. So you need to save that space for that content. And yeah, this is a little bit of explanation of how it goes. So basically subtract 4 and it should be like that. Okay, the order for the push was just 0 through 6, so you guys were okay with that. I noticed that few of you actually show the SP pointer, the stack pointer. You always need to show it. If it has nothing, the SP pointer is here. If you add only R6, it will be here. But if you do this, it will be directing to the lowest address where a content was added. So it will be directly here. If by any chance in the exam they try to put, say, another address direction here, but this location is empty, you're supposed to still put the SP pointer in the last content that you added, so that will be here. Even if they show something here, as long as this location of the content is empty, then the SP is going to be just on the last content added. Now this part is really important because it relates to the next push, which is you have to make sure that the last content that was added, so that will be R0 in this case, is going to be the first that's going to get out. It doesn't matter if R1, R2, or even R0 is there. Like the first that comes in, the first input, sorry, I mixed it up. But it is the last input goes to the first output that asks for it. And see, then you do the addition. Most of you didn't do the addition. Make sure that you know how to subtract and add. This is just an example of how I did this. Yeah, make sure to, oh yeah, this is an important part because I noticed that some of you confused this A and thought that we were talking about pairs. No, this is just hexadecimal representation for the number 10. When you write to the register, we don't write to it symbols. The only thing that is not a number that we write to it will be the letter that represents a number in hexadecimal, and this X that basically tells you, oh yeah, this is a 0x, is a hexadecimal number. Okay, so you do the subtraction, and well, based on what I explained for the question 1, I hope that helps you understand why this solution is what it is. If it doesn't, then I explain a little bit here. Basically, you're borrowing from the left side, and left side it was completely 0, so you have to cross the boundary at the top. Okay, now we come to the first pop. So it's important to notice that at the beginning, to keep a record of how many contents we're putting inside the stack and how many we're putting out. If you're doing a lab, I would recommend to always taking care of that, because if you have, say, 3 push and then you have just 2 out, and then you think that's okay for your code, that's not okay. You always need to have the same number of push and pop for your lab to code. If it doesn't, then it's not gonna work out at all, and your code is gonna like show you as if it was debugging, but it's actually not gonna do anything. It's not gonna go to any line, and you won't have any output. Okay, so right now you're just taking out 5 contents out. These were the ones that you were looking at. So what happens once they're out? The SP stays to the last content that you have in the stack, which will be R5. I wanted to write this just so you know what is in the main, because stack and main have different values, and you need to be aware of that, or else you will have mixed information. Because I noticed that some of you updated R5 once this pop happened, and this actually only shows values that are between 0 and 4. So register 0, 1, 2, 3, and 4. That's it. Okay, so I actually want to look back here, and I want you to notice that after that pop happened, yeah, you did have this addition, but your main point was, for this question in specific, was to know, how the stack looks after this push. And I want you to notice that you have R1, 5, 0, 2, 4, 3, but you don't have 6. So honestly, you don't even have to do that in this case, in this specific case. So be careful to know that so you don't waste time doing that addition. Okay, so let's go to this point, which was a point where a lot of people messed it up. And for some reason, let me copy this. Okay. So I want you to notice that you're adding 1, 2, 3, 4, 5, 6, and at this point you took 5 out, and originally you had 7 registers. That will help you to, make a logic check in case that you mess up. And now I'm gonna explain you what this part meant, because this was the biggest concern of everybody in the quiz. Okay, it's not copying, but it's alright. So basically, the last in is the first out. So this push that we just put inside is gonna be here at the end. And that will be, I think, our 0. Okay, so basically this push, that is the last one that we had, is gonna be at the top of the ones that we already had. So the order is not gonna be updated. You're not gonna have, oh, this R5 here, or this R0 here, if it was a highest order. Like, imagine if there was an R2 and you had the R5 here. This R5 would not replace the location of that R2. So now let's keep going. The ordering and how you put that content. So as I said before, the highest register goes to the highest address, and since we cannot replace the location of this one, we're gonna start from here. So the highest one we're gonna see, we have R5, R4, R3, R2, R1, R0, and that's how we say it. The highest, the lowest, and if I said before, this, boom, the stack pointer goes to the last content added, and the base is empty, and yeah, that's it. Which is more related to quiz 2, actually, is this point, which I recommend you to test how you do the stack and how that actually shows in your KL, which you might get tested on it in your quiz. So if you want to practice, you just go to your KL, you had a code where you do some push, and you go to your view memory window and get any memory that you want. So say that we start at a point that is, how do you know where it is? Okay, this is the SB, the stack pointer. This is where the it's not the initial actually. The initial, I believe, was 5, 9, 8. So it will be this is the base. It's gonna stay, as you can see, 0, 0, 0, 0. And we are already committed to push, so we save this value, 34. And you see that the order looks a little bit different. This is because of little ending. Actually, you have to review that information because it's gonna look a little bit different if you had something like 0x, 1, 2, 3, 4. It will be saved in the memory, I believe, as 34, and then 12, and so on. So be careful with that. I think it might be in your exam, probably, or in the quiz. So yeah. And so what you had in the code, we had this register, and then we saved that content into the stack, and this is the content. But as you can see, the address, is smaller. This is the original stack, and then as you add in content, the address gets smaller. So next time you add another push, that information is going to be saved here, and the address is going to be 2005090. So it's going to be 4 minus the existing address. Was more about these points, and honestly, I think you just need to have it in your crib sheet. I would recommend having the names so you don't get confused about their difference, and practice it with your kill because each one goes different. And let's see, this is the only one that I think might be worth explaining. How to use the LSL. What does that mean? So you're going to do a left shift of this register, and then you're going to add that to R1, and that's going to give